In this video, we're going to talk about intermolecular forces and their effects on the physical properties of organic molecules. Especially, we will focus on the effects on, boiling point, although that it will relate to melting point as well. This is a picture of a sample of butane that was taken from a broken grill lighter. You can see that here we have butane as a liquid, right? Butane has a boiling point of approximately -1 degrees Celsius. And so it's only a liquid here because in this container it is under pressure, right? It would normally be a gas at room temperature, right? We know that butane has a structure, right? 1, 2, 3, 4, right? Where there's a carbon at the end. I'm going to go ahead and show the hydrogens, roughly tetrahedral, right? Hydrogen here, hydrogen here, hydrogen here, there, hydrogen, 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 right? And even though there is a very slight, right, excess, right, carbon is just a teeny bit more electronegative than hydrogen, right? That would make this methyl group just slightly polar in that direction. But this methyl group would be just slightly polar in that direction. And this methylene group would be slightly polar in that direction. And this methylene group would be slightly polar in that direction. But here in its lowest energy conformation, right, these two vectors are pointing in opposite directions and therefore would cancel each other in the vector summation. And so there would be no effect, right? Similarly, these two vectors are pointing in exactly opposite directions. And so whatever slight polarity there might be within the group, that is canceled. And so overall, we have a non-polar molecule, right? But we have a non-polar molecule that can exist in the liquid phase, right? So even though it is non-polar, right, there must be some form of intermolecular forces. In order to hold the butane in this liquid phase, even under pressure. All right, so we're going to talk about the energetics of phase change here for just a second. So if we look at our butane, right, there are really two phases represented, right? As we noted down here, here is our butane in the liquid phase, right? It has a density of approximately 0.75 grams per milliliter. But also represented here is butane in the gas or vapor phase, right? At this temperature, it has a pressure of approximately 2 atmospheres. That's the equilibrium vapor pressure that would allow gaseous butane to be in equilibrium with liquid butane at about 20 degrees Celsius, just a little below room temperature, right? So it's approximately 2 atmospheres, which would give it a density of approximately 0.006 grams per cubic centimeter, okay? Which tells us something, right? That in the gas phase, right, in the gas phase, the molecules are very far apart. right? While in the liquid phase, the molecules are very close together. Right? So there's our liquid phase. Right? We have molecules very close together, right? Lots of molecules in the same space versus very few molecules in that space, right? And so we can see here the difference between the gas phase and the liquid phase, which leads us to consider, right, groupings of state, right? We can talk about the gas phase being a gas phase, but we can talk about liquids, right? Liquids and solids as condensed phases. Okay? So, to be clear, right? Condensed matter is any form of matter in which intermolecular forces are strong enough under the conditions of temperature and pressure right? We always have to specify our conditions to overcome the tendency of molecules to disperse due to the influence of preferred entropy changes. Right? So there's a lot of important information there, right, that we need to sort of think about, right? So we're talking about, right, the presence of intermolecular forces, right? But we've also got the influence of entropy, right? Entropy tends to try to disperse matter, right? Because if you spread the molecules out, there's more ways to distribute the energy, and that tends to be favorable, right? Having energy in lots of different places instead of energy concentrated in one place, right? So the natural tendency of molecules to disperse because of entropy tends to favor the gas phase. In order to maintain a condensed phase, right, we have to remember our condensed phases are the liquid phase and the solid phase, right, as our most common condensed phases, right? We must have some kind of intermolecular force that can overcome this tendency, right? So we'll focus a little bit on the energetics. We can go back to our standard Gibbs free energy equation, which is delta G is equal to delta H minus T delta S, right? Where delta G is the Gibbs free energy, right? And a negative Gibbs free energy is favorable for an overall process. Delta H is the change in enthalpy, which we can measure in terms of change in heat energy. Delta S is the change in entropy, right? And a positive change in entropy is favorable, right? So the positive change in entropy times the negative tends to contribute to a negative delta G, right? And then temperature is in Kelvin, right? And so we're talking about this term initially, right? And so we know that in general, the entropy for a gas is much greater than the entropy for a liquid, which is only a little greater than the entropy for a solid, right? And this gets back to what we talked about before, how spread out the molecules of a gas are. So going from a liquid to a gas is a positive entropy change, which makes this term very positive, right? So most liquids, from an entropy perspective, right, it's favorable to turn into a gas. That makes this a large positive number. That large positive number times this negative tends to make delta G negative, which means from an entropy perspective, vaporization is favored, right? Let me write that down. So vaporization is favored from an entropy perspective. Which means if we're going to keep something in a condensed phase, right? That is in the liquid phase, right? Where delta S is going in the unfavorable direction from gas to liquid, then we need a negative delta H to overcome the unfavorable delta S, right? Right? So to maintain a condensed phase, right, a negative delta H must overcome the unfavorable delta S for the condensation process, right? And so what is our source of that favorable delta H? If we go back to general chemistry, we can talk about the van der Waals equation. Right? And there are different ways of representing the van der Waals equation, but one is this, that the pressure is equal to, right, the number of moles times the gas constant R times the absolute temperature divided by the volume minus a factor, the number of moles times a constant B, minus the number of moles squared times the constant A divided by the volume squared, right? And, right, the van der Waals equation was developed by a Dutch physicist, J.D. van der Waals, who was Dutch, right, who received the Nobel Prize for physics in 1910 as a result of this work, right? And what van der Waals was looking at, remember, right, is describing the behavior of real gases and how they deviate from the assumptions we make with ideal gases, okay? And so, right, van der Waals looked at two things, right? One function was looking at the real volume taken up by particles of the gas, right, that tends to increase pressure relative to the ideal assumption because it reduces the volume in which the molecules can move. And that factor is right here, right? The space taken up by the molecules reduces the volume in which the molecules are allowed to move, which tends to increase the pressure, right? But there's also a second factor, right, that van der Waals recognized, right? That is that attractive forces between the molecules tend to decrease pressure because the collisions are not perfectly elastic. Some of the kinetic energy is lost in overcoming that attraction, right, relative to the ideal case, right? And that factor is this one here, right? Right? That's the factor that tends to decrease pressure, right? So van der Waals was able to identify and quantitate attractive forces between molecules, right? And relate those to, right, the decreases in pressure that you would see as a result of those attractive forces. Okay? If we plot the energy of those attractive forces, right, we get something that looks like this, right, where we get a plot where this is the distance between the molecules, right? Zero stabilization energy is here, right? This is energy, right? So let's extend our zero out there, right? And so when they're far apart, there's no stabilization energy. As they get close together, it begins to drop. It reaches a minimum, and then as you get them too close together, it asymptotically rises to zero, right? And this preferred energy we will call E0. And in general, right, the energy of the interaction is roughly proportional to, or roughly equal to, right? That preferred energy divided by the distance to the sixth power, right? The distance between them to the sixth power, right? So the attraction falls off very quickly as the molecules get farther apart. But it is this energy change, let's go to this, right? It is this energy change, right? This change in energy, which is favorable, it is negative, which is expressed as the delta H in that equation, right? So in our delta G equals delta H minus T delta S, right? We said that, right, the entropy change for vaporization is favorable. So the entropy change for staying in the liquid phase is unfavorable, right? It is negative, right? So a negative times a negative would tend to make delta G positive, unfavorable. So delta H, this negative energy change as a result of this attraction, it must be negative enough to overcome this unfavorable term, right? And so that is why intermolecular forces are so important to maintaining a condensed phase. Even the smallest and most nonpolar of molecules can form condensed phases, right? If we look, for example, nitrogen, right? Nitrogen has a boiling point of just a little higher than 77 Kelvin, right? Right? Hydrogen has a boiling point of just a little higher than 20 Kelvin, right? And helium, which is, right, a single atom acting as a molecule, by definition very nonpolar, has a boiling point of something very low, but still achievable at just a little above 4 Kelvin, right? And so, if they will form liquids, and they all will, right, below these temperatures, then there must be some source of intermolecular force, even in the most nonpolar of molecules, right? The source of that force, right, the hypothesis was proposed by Fritz London in 1930, right, who made a quantum mechanical argument to explain the attraction between even the most nonpolar of molecules, right? And we call those interactions London dispersion forces. Okay? So let's look at the source of London dispersion forces, or sometimes called London dispersion interactions, right? So let's go back to butane. And so each of these shapes represents the nonpolar butane, right? Where the blue dots roughly represent where protons are, right? Here are carbon atoms, right? The nucleus of carbon atoms. Here's the one proton in the nucleus of each hydrogen atom, right? And then the white here represents the electron cloud surrounding that molecule, right? And so it is the electrons on the outside that are available when two molecules are interacting, right? But as we bring these molecules close together, right, what can happen is that the distribution of electrons can be disrupted. That is, some of the electrons in this molecule momentarily get shifted so that a few more of them are on one side, making a partial negative charge, leaving an absence on the other side, a positive charge. But the effect of that momentary uneven distribution of electrons in this molecule, this positive charge tends to attract the electrons in this molecule. And so these electrons get shifted over, a few more on that side, and a few less on that side. And so for a moment, we get a weak electrostatic attraction. And when the sum of all of those weak electrostatic attractions occurring between molecules in a bulk sample of the material, right, those add up to what we measure as London dispersion forces, right? And so the greater the contact between molecules, right, the greater the surface contact, because remember, these fall off very quickly, right? As the distance increases raised to the 6th power, right? So any increase in distance lowers the effectiveness very quickly, right? And so if we look at this, right, if we look at something like pentane, right, 1, 2, 3, 4, 5, right? Pentane has a boiling point of about 36 degrees Celsius. Right? If we look at the same molecular weight, right, 1, 2, 3, 4, 5, isopentane, right, the presence of this methyl group here keeps them from packing as close together. So even though the molecular weight is the same, the boiling point is less, about 28 degrees Celsius. Right? And then if we look at neopentane, right? Neopentane is tetrahedral and it's roughly spherical. And so, right, its contact is even less effective and its boiling point is just a little less than 10 degrees Celsius, right? So we can see the effect of that reduced contact. A straight molecule where molecules can lie right next to each other to maximize contact has the highest boiling point. One branching, which reduces contact, reduces the boiling point. In this case, two branches reduces the boiling point even more, right? And so these interactions are sometimes called induced dipole interactions, right? Because conditions cause or induce a dipole to occur in one molecule, if only momentarily. But that influences an adjacent molecule to cause it or induce it to have a momentary dipole. And that creates the weak electrostatic attraction. Okay? So, we tend to get increased interaction with longer molecules and straighter molecules, that interaction is reduced as molecules branch. Observation shows us that polar molecules have stronger intermolecular forces between them than do nonpolar molecules. Right? And we can look at properties. Right? If we look at something simple like propane, right? Propane has a boiling point of about minus 42 degrees Celsius, right? But if we make just a small change and focus on dimethyl ether, right? We put an oxygen in the middle of that chain with the two methyl groups, and the boiling point goes up to minus 24 degrees Celsius, right? About 20 degrees higher. Right? But if we look at the same length chain and focus on acetaldehyde, right, which has a double bond O there, right? The boiling point for acetaldehyde is right about 20 degrees Celsius, right? And so here we have, right, the only difference between propane and the dimethyl ether is instead of a CH2 here, we have an oxygen. Oxygen is more electronegative than carbon, which tends to create, right, a little bit of a polarity vector in the molecule in that direction, right? And that little bit of polarity is the difference, right? In the acetaldehyde, that C double bond O has a stronger polarity vector in that direction, right? And so something about being polar strengthens the intermolecular forces. And we call those dipole interactions. Right? So if we focus on acetaldehyde, right, we have our carbonyl, right, with, right, our CH3, which our methyl group is going to be relatively nonpolar, right? That creates a dipole, right, where the oxygen is carrying a partial negative charge because it's more electronegative, and the carbon is carrying a partial positive charge. And if we have another one of those molecules close together, right, close to the first one, again with the same kind of partial negative and partial positive charge, then we're going to get a weak attraction between the two molecules as the negative charge attracts the positive charge. And this is stronger than a London dispersion interaction because this charge separation is permanent because these molecules are polar, right? So we have a permanent charge separation, even if it's not complete, and that means we always have an attraction between these two molecules and between any other two, right? The negative of any molecule is going to be attracted to the positive of any other molecule that gets close to that. And so dipole-dipole interactions are stronger than London dispersion interactions. Okay? So anytime we have polar molecules, we can express, right? We can expect that they have dipole-dipole interactions. Those are going to be stronger than London dispersion interactions, and those will have predictable effects on the physical properties, in this case, boiling point. So another class of interactions has to do with this observation, right? That molecules in which hydrogen is bound to a strongly electronegative atom have stronger intermolecular forces than do other polar molecules. For instance, right, if we go back and look at our polar molecules, our dimethyl ether, right, that had a boiling point of minus 24 degrees Celsius. And if we look at our acetaldehyde, where we had our more polar carbonyl, right, and it had a boiling point of about 20 degrees Celsius, right? If we look at ethanol, right, where we have a hydrogen bound directly to a strongly electronegative atom, right, that has a boiling point of about 78 degrees Celsius, right? So we can see this trend, right? And we attribute that to a special kind of dipole-dipole interaction that we call the hydrogen bond. Right, sometimes abbreviated H bond, right, that was discussed in different contexts by different chemists between about 1912 and about 1920, right? So in order to get hydrogen bonding, right, you need, one, a hydrogen bound to a strongly electronegative atom, right? And the things that count as strongly electronegative are nitrogen, oxygen, fluorine, and chlorine, right? Some books will include sulfur, right? Sulfur is highly polarizable, but it's not really electronegative enough to count, right? And given that these two only make one bond with hydrogen, right, their utility is sort of limited. And so we tend to focus on hydrogens bound to nitrogen and oxygen within organic structures, right? So that's the first thing, right? The second thing, right, in the other molecule, you need a strongly electronegative atom with an unshared pair of electrons. Right? So again, we're talking about this same group, same qualification there, right? So you need an electronegative atom with a hydrogen bound to it in one molecule. And in the other molecule, you need a member of that same electronegative atom group with an unshared pair. And you get an attraction that is stronger than a dipole-dipole interaction. As a matter of fact, if you measure the E to E bond distance in the hydrogen bond, it is less than the sum of the E to hydrogen to E van der Waals radii. Right? So it is an attraction where these atoms are pulled closer together, right? Then the sum of the van der Waals radii suggests that they should be able to be pulled together. All right, so the hydrogen bond is really something special over and above a dipole-dipole interaction. And therefore, it is stronger than a dipole-dipole interaction. Right? It is strongest if the electron density of the bond between this electronegative atom and hydrogen lines up directly with the electron density of the unshared pair, right? So there is a preferred geometry where there is a straight line between this electronegative atom, the electrons of the sigma bond, the hydrogen, the electrons of the unshared pair, and the nucleus of this electronegative atom. Those all need to be in the same line for the hydrogen bond to be its strongest. Okay? Now note, when we're talking about this, right, the molecule that has the hydrogen bound to the electronegative atom, we call that the hydrogen bond donor group. The electronegative atom that has the unshared pair in the other molecule is the hydrogen bond acceptor, right? So we can look in molecules to find hydrogen bond donor groups and hydrogen bond acceptor groups, okay? Right? So intermolecular forces can occur between like molecules or between unlike molecules. Right? And when we start considering interactions of molecules that are different from each other, right, we get some other possible interactions. For example, right, we can have a dipole, induced dipole, interaction or attraction, right? That is when we have a polar molecule interacts with a nonpolar molecule. Right? So if we have the polar molecule, right, with a permanent negative, positive separation because of electronegativity differences within the molecule, right? And we have a nonpolar molecule nearby, right? The presence of that negative charge, right, can chase the electrons away, right, can repel the electrons in the electron cloud, creating a partial negative, right, a partial negative and a partial positive, right? And because this is a permanent dipole, right, this movement is stronger than in our London dispersion interaction, and we get a stronger interaction, right? So this kind of interaction is stronger than a London dispersion interaction. But weaker than a typical dipole interaction, right? And so we can make predictions for intermediate types of interactions based on the properties of the molecules that we're dealing with, right? So we have to be able to, again, look at molecules, determine what molecules are polar and what molecules are not, and then predict how those molecules might interact. So we've got a lot to consider. This was a long video, but these are very important concepts that we have to be able to think about when we look at molecules and think about how they might interact with each other in condensed phases especially. Okay?